Hey, welcome to the last video about momentum. In this one we're going to look at two-dimensional collisions. And here, AP is not going to ask you really difficult problems about collisions in two dimensions, but they can get extraordinarily difficult sometimes. And we're going to work some relatively easy ones, look at some special cases, but you will have to know the basics, but you're not going to get a really difficult 2D problem on an AP exam. Now, when you have a 2D collision, it's just like one-dimensional collisions. Momentum will be conserved. If it's elastic, kinetic energy will also be conserved. But the thing is that the x component of the momentum is conserved, and the y component of the momentum is also conserved. And so whereas for one-dimensional collisions we had m1 v1I plus m2 v2I equals m1 v1f plus m2 v2f. Now that's still going to be true for two dimensions, but in two dimensions, the fact that it's a vector equation means that it gets split up into two parts. You have m1 v1ix, the subscripts are getting complicated here, m2 v2ix equals m1 v1 fx. I should not be writing the vector signs there because the x component of a vector is not a vector in itself. m2 v2 fx. And similarly for y, and I will actually go through and write this down, although I don't really know why I am. Basically, it's the exact same equation, but with y's substituted for all the x's. So you have two different equations for momentum conservation. If energy is conserved, then you'll have a third equation for kinetic energy, and you can see where this is going to become complicated. You will not have to solve elastic collisions in 2D. The AP syllabus specifically says that. And because there are more variables, you have an x and a y component of every velocity, so now instead of 6 variables we have 10, but still only 2 equations. You generally need more information to solve than in one-dimensional collisions. And here's an example. You have two balls, A and B, they have different and unknown masses that collide. So initially, A is at rest and B has speed v. So A is at rest and not moving. B has speed v, that's before the collision. I'm just going to say v is moving in the positive x direction. Now after the collision, B has speed v2, and it's moving perpendicularly to its original motion, so we'll say it goes upward. Now if we think about conservation of momentum, we want to find the direction that ball A moves after the collision. If we think about the conservation of momentum, the question is, which way does A go? The change in B's momentum, so there's B's initial velocity, and there's its final and there's the final velocity. So that means the change in B's velocity points in that direction, and so does its change in momentum. So A has to pick up some momentum in this direction in order to keep the momentum conserved. And there's a couple ways to do this. First off, we could just find this angle here, and that would be the same as this angle here. But I'm not sure I can explain that well, so we're going to brute force it a little bit. We're going to try to find the angle that vector VA makes with the x-axis. So we will now set up conservation of momentum in the x direction. The initial x momentum is mv times v, And after the collision, B is not moving in the x direction at all, so it has no x component of its momentum. And the x component of A's momentum is ma VA times the cosine of theta. So there's one equation. And then for the y components, we'll notice that initially neither ball is moving in the y direction, so 0 goes on one side of the equation. And on the other side, we have the y component of B's momentum, so that's mb times v over 2, plus the x component, or the y component of A's momentum, which is downward, so we'll make it negative, ma VA sine theta. And now we'll say, okay, we'll solve this equation. We'll say mb times v, because we don't know either one of those, equals 2 ma VA sine theta, because what we're doing is we're looking for theta. That means we want to get rid of everything else, because we don't know anything else. And then what we'll do is we'll take this and we'll substitute it in there, which is going to give us 2 ma VA sine theta equals ma VA cosine theta. Divide the entire equation by ma VA, do a bit of algebraic manipulation, sine theta over cosine theta equals 1/2. And of course, that's tangent theta, so we can say that theta equals the arctangent of 1/2, which is about 27 degrees. And so A's final velocity is 27 degrees below the x-axis. We could have gotten this by using the exact same equation. We could have gotten just by using that triangle, and I'll let you figure out why, but we brute forced it, and it really wasn't that difficult. Now, well, it wasn't that difficult if you've worked a lot of these problems. So that's something you need to do. But before you start working on question 9, I want to look at a special case, and that is an elastic collision between two identical particles and one of them is originally stationary. So before the collision, you have particle 1 moving with speed v, particle 2 stationary. After the collision, you have particle 1 moving in that direction, speed v1, particle 2 moving kind of that direction with speed v2. And we want to know, there's something we can see about v1 and v2. So the first thing that we can say, because they both have the same masses, mv equals mv1 plus mv2, using this as a vector equation. Divide by m, and we find that v as a vector equals the vector sum of v1 and v2. So what that means is that we can draw a triangle. We have v1, and we have v2, and we have v. So v1, v2, and v can all form a triangle. If we apply conservation of energy, because it's an elastic collision, we'll find that the 1/2 mv squared equals 1/2 mv1 squared plus 1/2 mv2 squared. So we can divide the entire equation by 1/2 m, and we get v squared equals v1 squared plus v2 squared. So what we have is a triangle in which that relationship holds. And if we look at it closely, what kind of triangle satisfies this equation for the side lengths? And it's a right triangle. And the result is, if this is a right triangle, that v1 and v2 are perpendicular, which is kind of cool. This isn't going to be on the AP exam, but it's an example of the kind of reasoning you sometimes have to use in physics. But do notice that this is not a general case. The collision had to be elastic, and the two particles had to have the same mass, and the first one and one of them had to be stationary. So lots of caveats, but it's still pretty cool. Tomorrow, do question 9. You should be able to do all of the chapter 10 questions at this point.